So in three-dimensional geometry, another important derivation that we come across is the equation of a plane in the normal form. This is the first derivation in the plane. So here we are going to find out the equation of a plane in the normal form, both in the vector and Cartesian form. Okay. So consider the rectangular coordinate system x, y and z axis. So consider a plane in the rectangular coordinate system. Let the plane be at a distance d from the origin. Let the plane be at a distance d from the origin. So I am taking a plane in the rectangular coordinate system. Let the distance of this plane be d from the origin. Let ON be the normal. Let vector ON be the normal to the plane, and n cap be the unit normal vector in the direction of vector ON. So we get vector ON is equals to n cap into d, because the length of the ON is d and n cap is the unit vector along that. So vector ON will be equal to n cap into d. Now take any point P on the plane. Take any point P on the plane. Any point P on the plane. With the position vector of OP as vector R. Okay, I am taking a point P here. The position vector of this vector be vector R. Now because ON is perpendicular to the plane, and if you take NP on the plane, so naturally NP will be perpendicular to ON. Okay, so clearly NP is perpendicular to OP. ON. So if two vectors are perpendicular according to the dot product, NP vector dot ON vector must be equal to 0. And NP vector can be written as OP vector minus ON vector dot ON vector is equals to 0. That is, if I write here, that is OP vector is vector R minus vector ON. Here it is n cap into D. So n cap into D dot ON dot n cap into D is equals to 0. Now using the dot product, vector R into vector R dot vector n cap into D minus n cap dot n cap into D square equal to 0. But here n cap is a unit vector. N cap is the unit vector in the direction of, here we have written, n cap is the unit vector in the direction of vector ON. So n cap dot vector n cap will be equal to 1. Equal to 1. Then above equation reduces like this. R dot n cap into D minus D square equal to 0. If I take D square on the other side, R dot n cap into D is equal to D square, and that is equals to R dot n cap equal to D. Now this is an equation of the plane in the vector form. Okay, so here vector R is the position vector of the point P, and the n cap is the unit normal vector along the direction of vector ON, and D, it is the distance of the I can call it as a perpendicular distance of the plane from the origin. Okay, now this is the vector form of the equation of the plane. This is the vector form of the equation of the plane. Okay, now the same equation we are going to derive in the Cartesian form. Okay, so keep this equation of a plane in the vector form as it is in your mind. Now let us derive the Cartesian form of the plane. Okay. So here point P is some arbitrary point. So for Cartesian form, let us take the coordinates of P as x, y and z. So vector R will be equal to xi cap yj cap plus zk cap, and whereas vector n cap is a unit normal vector, so that's why using the direction cosines I can write n cap as n I cap plus m j cap plus n k cap, where L, M, N are direction cosines. Okay, then I'm going to substitute these two values into that equation now. Okay. I'm going to write that equation as it is. Vector r dot n cap is equals to d. So r I have here is xi cap plus yj cap plus zk cap dot n cap. Using the direction questions I have written here like this: li cap mj cap plus nk cap is equals to d. Now again, using the dot product of two vectors, we get like this: lx plus my plus nz equal to d. Now this is the equation of the plane in the Cartesian form.